All right, so you've had a couple minutes now to take a look at these differential equations and classify them. I've got them classified up here. The first example, this is ordinary because the only independent variable here that we can see is x, or the only derivative we've taken with respect to is x. So it is ordinary. It is a first order since only the first derivative is present, and it is linear, as nowhere do I have y times y or y derivative of y times a derivative of y, none of that stuff. The second one, now I've used a different notation here. This is requiring us to remember. We've probably seen it most often in a physics class, but this dot notation, the dot means derivative. So y dot is the first derivative of y. Y double dot is the second derivative of y. This is an ordinary differential equation, as we're not told what the independent variable is, but we have to assume that it's the same. Otherwise, whoever wrote this would have clarified. And based on the right-hand side, we can assume that the independent variable is x. But the only derivative that's been taken is of y, and we have to assume it's with respect to the same independent variable. Thus, this is an ordinary differential equation. I see a second derivative present, so it is a second order differential equation. And since I have a derivative of y times a derivative of y, that is the second derivative is squared in this case, this is nonlinear. Moving on to the third example. Now I have x prime and y prime. It doesn't clarify what the independent variable is. So once again, I have to assume it's the same. Otherwise, they would have clarified. So this is an ordinary differential equation. The first derivative is present, and it's present, the first derivative of x and the first derivative of y, but those are still first derivatives. Thus, this is a first order differential equation, and it is nonlinear since in each case I have a derivative multiplied by itself. So this is a nonlinear differential equation. Moving on to the fourth example. This is a partial differential equation since I've taken a derivative with respect to y and a derivative with respect to x. I don't really care beyond that. I just see I've got a derivative with respect to y and a derivative with respect to x. So it's that's more than one. So this is a partial differential equation. I see a second derivative, so it is a second order differential equation. And at no point do I have a derivative of u multiplied by itself or derivative of y multiplied by itself. So this is linear. So now let's revisit solutions. You remember I mentioned that we've always said something is a solution if it makes the statement true. And we test this out in algebra by saying something like 2x minus y equals 0. It's a solution if I plug in the value for x and plug in the value for y and get a true statement. So let's apply this rationale to a differential equation. So let's go back to the differential equation dy dx plus 5y is equal to e to the x. This was a first order linear differential equation. And maybe we're asked verify that y equals 1/6 e to the x solves this differential equation. This means I need to plug this into here to see if I get a true statement. So I'm taking the derivative with respect to x of y plus 5y's, and that needs to be equal to e to the x. That's what I'm testing to see if it's true. Well, the derivative of e to the x, as we all know, is e to the x. The derivative of 1/6 e to the x is 1/6 e to the x. 5 times 1/6 e to the x is 5/6 e to the x. Again, I'm testing to see if that's equal to e to the x. Well, 1/6 of something plus 5/6 of something is in fact equal to 6 of those sixths. So we get 1 full e to the x is indeed equal to 1 full e to the x it checks out. This is a solution to the differential equation. Maybe we want to take this same differential equation, y dot plus 5y e to the x, and maybe we want to verify that y equals 5e to the negative 5x solves this differential equation. Again, I'm just going to plug it in and see if I get a true statement. So I need to take the derivative with respect to x of y, which was 5e to the negative 5x, adding back in 5y's, which was 5e to the negative 5x, and I want to check to see if that is in fact equal to e to the x. The derivative of this is the derivative of e to the negative 5x is e to the negative 5x times the derivative of negative 5x, which is just negative 5. So this is negative 25 e to the negative 5x plus 25 e to the negative 5x. And I'm checking to see if that's equal to e to the x. Well, on the left, I have, in fact, 0. And 0 is not equal to e to the x. So this does not solve the differential equation. That is not a solution. One last example. Maybe we want to verify that y equals c1 cosine of t plus c2 sine of 4t. Let's change the argument on this first one to be cosine of 4t as well. So c1 cosine of 4t plus c2 sine of 4t. And we want to verify that solves or is a solution to y double prime plus 16y equals 0. Again, checking to see if it solves means just plugging it in. The second derivative of cosine is negative cosine. The second derivative of cosine of 4t is negative 4 times 4 times cosine of 4t, so negative 16 cosine 4t. So y double prime here is negative 16 c1 cosine of 4t minus 16 c2 sine of 4t. Feel free to work that out on your own if you don't believe me. And what I want to check to see is if y double prime plus 16y is equal to 0. Y double prime plus 16y is negative 16 c1 cosine of 4t minus 16 c2 sine of 4t. And then I'm adding to that 16 y1s, or sorry, 16 y's. So 16 times c1 cosine of 4t plus c2 sine of 4t. Well, I have negative 16 c1 cosine 4t on the first part. I have a 16 c1 cosine 4t on the second part. Those do indeed zero out, and the same happens for sine. And so we can indeed verify that that solves this second order linear ordinary differential equation. We could imagine being given that this is a solution to the differential equation and then being told to find the values of C1 and C2 such that this solution passes through a given point. We did that in Calc BC all the time, right? We would be given the differential equation, something like dy dx is equal to x, and then we would find the general solution where we had a C value, that constant of integration, and then we would find the value of that C so that it went through a specific point. We would be finding the particular solution. Same thing applies here. So we can imagine being asked to do that. This solution here, it has a C1 and a C2. We call this a two-parameter family of solutions. Or a two-parameter general solution. Because there are two things we don't know, C1 and C2. Up here, there were no parameters in this because this was a particular solution. There were no parameters in this. This was a particular solution. In this case, we have parameters, so this is a family of solutions. All right. One thing that mathematicians and philosophers have in common is a concern about existence and uniqueness. Not only do we exist, but are we unique in that existence? So let's address that. Let's address that in terms of differential equations. If we let R be defined as the set of xy such that A is less than or equal to X is less than or equal to B, and C is less than or equal to Y is less than or equal to D, and we have the point x naught, y naught contained in R. If f and the derivative of f with respect to y are continuous on R, then there is some interval I containing x naught, y naught, with I being a subset of the closed interval a to b. And there is a unique y of x on that interval, solving dy dx is equal to f of xy, such that y of x naught is equal to y naught. So that's our this is called an existence theorem because it says if certain conditions are met, then something exists. If these conditions are met, that is f and fy are continuous, then there exists a solution. It's also a uniqueness theorem because not only does one exist, but it is unique. So this is called the existence and uniqueness theorem for solutions to differential equations. We're not going to spend really a lot of time dealing with this. I'll leave that to a future analysis teacher of yours. Suffice it to say, this is the thing which says, yes, a solution exists to be found. So let's remind ourselves, let's practice finding a solution. Not finding a solution. Actually, you know what? Let's find a solution. Find, say, R such that y equals e to the rx solves the differential equation 2y double dot plus 7y dot minus 4y equals 0. So we want to find an R so that this solves this differential equation. So if y is e to the rx, then y prime is r e to the rx, and y double prime is r squared e to the rx. Plugging this into the differential equation gives us 2 times r squared e to the rx plus 7 times r e to the rx minus 4 times e to the rx, and that needs to be equal to 0. Let's clean this up a little bit. I can take an e to the rx out of every term, giving me 2r squared plus 7r minus 4, and that has to equal 0. Now, e to the rx is never 0. No matter what r is, e to the rx is never 0. That means it must be true that 2r squared plus 7r minus 4 equals 0. This is just solving a quadratic. We've been solving this for years at this point. This is 2r squared plus 8r minus r minus 4 equals 0. I can take a 2r out of both of these, giving me r plus 4, and a -1 out of the last two, giving me an r plus 4. Now I can take an r plus 4 out of both terms, telling me that either r equals -4 or r equals 1/2. So we did find an r value which solves this differential equation. And in fact, we found 2 of them. There are 2 different r values which make this true. That takes us up to the end of today's material. We have covered 1.1, 1.2, and 1.3 today.